3.2 is on the characteristics of polynomial functions. Now, when I start this lesson, I just want to give brief introduction and then go on to some examples. So let's say I have just drawing an xy axis here and trying to start off with a very simple function which has an odd degree. Okay, so an odd degree function would be, an example would be f of x equals, say, 2x cubed plus 5x squared plus 2. So you can see here that the degree is odd. And odd number. So odd numbers are, numbers like 1, 3, 5, 7, and so on, right? And this number here, which is the coefficient of this term that has the highest degree, is called the leading coefficient. Okay, so that's another new word, or I could just call it LC for short. The leading coefficient is a positive number here. It's positive 2. So a very basic parent function that would have an odd degree and a positive leading coefficient would be the parent function f of x equals x. So if I were to draw a rough sketch, that would be a line something like this, right? That was f of x equals x. And before I go further, I want to name these quadrants. This is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So if you have this function f of x equals x, you can see that it has an odd degree because it's 1, and it has a positive leading coefficient. So what are some characteristics that you notice if a function has an odd degree and a positive leading coefficient? What are some other characteristics you notice? Is that it will always go from quadrant 3 to quadrant 1. Okay, the graph will be going from Q3 to Q1. I'm going to put arrows at the ends to show that it goes on infinitely in those directions. And what if it was an odd degree but a negative leading coefficient? What if your function was f of x equals negative x? So let's draw a rough sketch of that line. It would be something like this, right? This is f of x equals minus x. F of x equals minus x. So it has a odd function with a negative leading coefficient, because the leading coefficient is negative 1. So what happens if it is, what quadrants does it go? Is it going? The function is odd degree and negative leading coefficient. You can see that it goes from quadrant 2 to quadrant 4. So this is kind of your foundation, that you always want to remember these trends, these characteristics, because they hold true for all odd degree functions of positive or negative leading coefficients. So for example, if I took the cubic function and let's say I did the y equals x cubed function, it would look something, say, like this. Okay, so this is f of x equals x cubed cubic function. You can see that it's a positive leading coefficient. The degree is 3, which is an odd degree. It goes from Q3 to Q1, just like this, right? Whereas if it was f of x equals negative x cubed, maybe it would go look something like this. Like it'd go like that, and it would be y equals, say, negative x cubed. It would go from quadrant 2 to quadrant 4, just like f of x equals minus x. Okay, you could also have a cubic function that doesn't have this shape. Sometimes you could have, say, a cubic function that is like this. Say this could also be a cubic function. And you can see it's going from quadrant 2 to quadrant 4. So just by looking at that behavior, that going from quadrant 2 to quadrant 4, you know that it's going to have a negative leading coefficient. So this one's going to have a negative leading coefficient, and it's going to be an odd degree function with a negative leading coefficient. Okay. So what are some of the conclusions we made is that if you have an odd degree function and your leading coefficient is positive, then it goes from Q3 to Q1. If it's a negative leading coefficient, it goes from Q2 to Q4, right? Let's look at also now the end behaviors. So what happens when x approaches positive and negative infinity? So if you have, again, the end behaviors depend on if the leading coefficient is positive or negative. Okay, so let's look at, we're only looking at odd degree functions. Okay, so let's take f of x equals x, which is this line here. As x approaches infinity, y also approaches infinity. As x approaches negative infinity, y also approaches negative infinity. So if x approaches infinity, y also becomes more positive. When x approaches negative infinity, y also approaches negative infinity. And that's if it is a positive leading coefficient. Okay. If it is a negative leading coefficient, what is the end behavior? So for the negative leading coefficient, let's take this line here, f of x equals minus x. As x approaches positive infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. Okay, so when x becomes more positive, y becomes more negative, right? And when x becomes more negative, y is approaching positive infinity. So that's the end behavior based on if the leading coefficient is positive or negative. We also want to look at now what does it look like for a function that is an even degree function. So we looked at odd degree functions. Now we're going to look at even degree functions and see their characteristics. So I'm going to draw a grid here and take a very basic function. Let's take the quadratic function. I'm just going to just draw this line better. Okay, so let's say this is a y equals x squared function, parent function for quadratic function. Y equals x squared. So y equals x squared is even degree function, because you can see the degree is 2, which is the even degree, and it has a positive leading coefficient. So what are the quadrants you see this one in? This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So if you look at the quadrants, it goes from quadrant 2 to quadrant 1, right? These two quadrants. If you were to graph y equals negative x squared, it would be the parent function but reflected in the x-axis. So this would be y equals negative x squared. And this one is an even degree function, and it has a negative leading coefficient. And you can see that it goes from quadrant 3 to quadrant 4. So that's the behavior of an even degree function when the leading coefficient is positive and the leading coefficient is negative. You can also have other even degree functions. For example, you could have a quartic function. So I'm just going to draw one quartic function. Let's say you have a quartic function and it's like this. Okay, let's say it's like this. This is your function. And you can see that, it's going from Q2 to Q1. So we know it's going to have a positive leading coefficient because it's going from quadrant 2 to quadrant 1. And a possible equation for this would be, let me do that in green itself. A positive equation could be like y equals, let's say these are the 4 zeros that you can see. These are the 4 zeros of this function. So let's say this is negative let's say -3, this is -1, this is 2, and this is 4. Let's say those are the zeros, okay? So then a possible equation would be y equals some a value which is positive, and then x plus 3, because that's the 0, x plus 1, x minus 2, and x minus 4. Could be a possible equation for that quadratic function, okay, where you have a positive leading coefficient. You could also have a even degree function that's quadratic and it opens down. So let's say I draw one like this. Say I draw one like this. This is an even degree quadratic function, which is going from quadrant 3 to quadrant 4. So this has a negative leading coefficient because it's going from quadrant 3 to quadrant 4. Okay, and what would possibly the zeros be? Let's say this point was -2 and this point is +2. Then a possible equation for this could be y equals some -a. And because it's only touching the x-axis, it could have double roots. So this could be x plus 2 squared, and this could be x minus 2 squared. So you can see that 2 plus 2, the degree is 4, and it has a negative leading coefficient, so it's going from quadrant 3 to quadrant 4. What is the end behavior of these even degree functions? Let's look at the end behavior. So if it is a positive leading coefficient, what is the end behavior? Well, when x becomes more positive, as you can see here, for y equals x squared, y also becomes more positive. And as x becomes more negative, which is on the other side, y is still becoming more positive. So both of them are y is leading to positive infinity. So it's the same end behavior, right? Because they both y values are approaching positive infinity. And if it's a negative leading coefficient, so you can see over here, let's take the quadratic when it opens down. When x becomes more positive, y is becoming more negative infinity. When x approaches negative infinity, y is again becoming more and more negative. So x approaches plus or minus infinity, y is approaching negative infinity. So again, it has the same end behavior, okay? So I wrote both of them in one step instead of writing them in two. So whether it's x is becoming more positive or more negative, y is approaching negative infinity. Another thing I want to look at is the turning points. Okay, so if you have an odd degree function, let's say you have a function that's odd degree, and for a line, of course, there's no turning points. Let's take the cubic function. This is an odd degree cubic function, y equals x cubed. There is no turning points, right? So for y equals x cubed, there is no turning points. The turning points are basically the points where you have a maximum or a minimum. That's where the graph changes from increasing to decreasing or decreasing to increasing. There's no such change here, so therefore there's no turning points. But you would have a cubic function that could be, let's say, like this. This could be a cubic function, and it has 1, 2 turning points, right? It's going from Q3 to Q1, so it is going to have a negative leading coefficient, and it has, so this one has got 2 turning points. Okay, so what we can see is a polynomial with n degree can have up to n minus 1 turning points. Okay, so write that down here. A polynomial with degree n can have up to n minus 1 turning points. And we saw that for a odd degree polynomial function. And for an even degree, let's say you have an even degree function and you want to see the turning points for that. Let's say it is an even degree function like this, like a quadratic function, right? It's even degree with a negative leading coefficient, and it has 1, 2, 3 turning points, right? That's the maximum it can have, and it has a degree of 4. So the n is equal to 4 in this case. The leading coefficient is negative, but it has 1, 2, so maximum, minimum, maximum, so 3 points. So for n equals 4, you can have a maximum of n minus 1 or 3 turning points, okay, as you can see over here in this example. Another thing I wanted to look at is also the zeros of a polynomial function. So if you think of a odd degree function, let's take the, an odd degree function, classic example is the straight line, right? Y equals x, okay? Odd degree function. And you can see that it has to cross the x-axis at least one point because it's always going from either Q2 to Q1 or Q3 to Q4. So an odd degree function, now it must have a minimum of 1, 0 because it has to cross the x-axis at least one point. It must have a minimum of 1, 0. Okay, so this one has 1, 0. If you have like a cubic function, again, it's crossing it at one point here, so 1, 0. Or you could have like a cubic function like this, right? And it has 1, 2, 3 zeros. So minimum, it has to have at least 1, 0. Then here in this case, it has 3 zeros, so it's at least 1. Whereas for an even degree function, you could have a function with, let's say, a quadratic function that's like this, y equals x squared, and it has just 1, 0. Or if I were to graph it, say, a little bit down, let's say like this, right? It can have this and this. It could have 2 zeros, right? Or if a quadratic was graphed like this, it could have no zeros because it doesn't touch the x-axis at any point. So it could have 1, 2, or none. So the even degree functions, you can have a maximum for n, for a degree of n, you can have a maximum of n zeros, right? And a minimum of no zeros, right? So the maximum you can have is n, and the minimum you can have is none. Whereas for an odd degree function, the minimum you can have is 1 because it has to cross at one point, and the maximum you can have is n. Like in this case, it's cubic, and you have degree 3, and you have 3 zeros. Okay, so let's do some practice questions over here. You have f of x equals x cubed minus 2x. As you can see, it is an odd degree function, and so its degree is 3. Is it even or odd degree? Well, it is odd degree. Now, this should not be confused with odd functions. Okay, we've also learned even and odd functions. That's not the same as odd degree function and even degree. They're two different things. Don't confuse the two. The leading coefficient here is x cubed. Its leading coefficient is positive. And the end behaviors are when x becomes, approaches infinity, y is approaching also infinity. When x approaches minus infinity, y approaches minus infinity. And it has 1, 2 turning points. Okay, so n minus 1, 2 turning points. The symmetry is asking you if it is an even function, an odd function, or neither. Okay, so if you look at this function here, you have to find f of minus x. If f of minus x equals f of x, then it's an even function. If f of minus x equals minus f of x, it's an odd function. And if both of them are not satisfied, it's neither. So if you did f of minus x, it would get minus x cubed minus 2 times minus x, which would be negative x cubed plus 2x. Factor out the negative and you get x cubed minus 2x. So it's minus of f of x. So if f of minus x is equal to minus f of x, that means it is an odd function. So the symmetry is odd. It's an odd function. It's symmetrical about the origin, which means if you reflected this function horizontally and then vertically, you will still end up with the same shape. Second example, this is your polynomial function. You can see the degree is 3, and the degree is 3 is an odd number, so it's odd degree. The leading coefficient is negative. That's why it goes from quadrant 2 to quadrant 4, like, you know, like y equals minus x. Think of that line, right? It goes from quadrant 2 to quadrant 4. And the end behaviors as x becomes more positive, y is becoming negative, and x becomes more negative, y is becoming more positive. And if you try to do the number of turning points, well, it doesn't have any maximum or minimum, so there is no turning points for this. And the symmetry, well, you have to check f of minus x, what that works out to. So it's minus 2 of negative x cubed plus 4 times minus x squared minus 3 times minus x minus 1. So that works out to 2x cubed plus 4x squared plus 3x minus 1. And even if you try to factor out the negative, you would get minus 2x cubed minus 4x squared minus 3x plus 1. And that's not equal to negative f of x or f of x. So there is neither an even nor an odd function, so it's none. So it's not odd or nor even function. Okay. It goes from quadrant 2 to quadrant 4, which makes sense because its leading coefficient is negative. Okay, next example here, you have a degree 4 function. It is even degree. The leading coefficient, as you can see, is plus 3, so it's positive. So you know when it's a degree 4, it's like your y equals x squared graph, right? It's positive, so it has to go from quadrant 2 to quadrant 2 to quadrant 4, right? And so quadrant 1, right? Quadrant 2 to quadrant 1. And behaviors, as x becomes more positive, y is becoming more positive, and as x becomes more negative, also y is becoming more positive. There is 1, 2, see how many turning points does this one have? It has only 1, 2, 3 turning points. And for symmetry, well, you have to do f of minus x. And f of minus x equals 3 times negative x to the power 4 minus 4 times negative x cubed minus plus 5 times negative x plus 5. There's also a plus minus 4 times negative x squared. Okay. So it works out to 3x to the power 4 plus 4x cubed minus 4x minus 5x plus 5, and so it's not equal to f of x or minus f of x. So its symmetry is it's none. It's neither even nor odd. Okay. Here you have degree 4. The function is of an even degree, and the leading coefficient is negative, so it makes sense that it has to go from quadrant 3 to quadrant 4. And so this is like your y equals negative x squared graph. It opens down, the quadratic opens down, it goes from quadrant 3 to quadrant 4. And behaviors as x becomes more positive, y is becoming more negative. X becomes more negative, also y is becoming more negative. So same end behaviors, turning points 1, 2, 3. So 3 turning points. And if you tried f of minus x to find symmetry, you get minus of minus x to the power 4 minus 2 times minus x to the power 3 plus minus x squared plus 2 times minus x. And you'll find that this, is not equal to negative f of x, and it's not equal to f of x. So its symmetry is none. It's neither odd nor even. Here you have a degree 5. So it's an odd number, odd degree function. Leading coefficient is positive. So it's like your y equals x graph that goes from quadrant 3 to quadrant 1. And end behavior, x becomes more positive, y becomes more positive, and x becomes more negative, y becomes more negative. So it has the opposite end behaviors. And it has 1, 2, 3, 4 turning points. N minus 1, degree 5, and 5 minus 1, 4 turning points. You'll find that its symmetry is also none. It's neither odd nor even when you work out f of minus x. This one here, degree is 5. That's an odd degree, and the leading coefficient is negative. So this is like your y equals minus x, like line which goes from quadrant 2 to quadrant 4. And its end behavior is x becomes more positive, y becomes more negative, and x becomes more negative, y becomes more positive. So opposite end behaviors. And it has 1, 2 turning points, and you'll find if you did f of minus x, it will not be equal to minus f of x or f of x. So there will be, it's neither an odd function nor an even function. So we'll try an example here. For each of the functions below, you have to say if, describe the end behavior and discuss the possible number of turning points and zeros and sketch a possible graph of the function. So this is f of x equals x to the power 4 plus 2x squared plus 1. So it's a quartic function, degree 4, positive leading coefficient. So, like your y equals x squared graph. So it has to go from quadrant 3 to quadrant 4. So, the end behaviors would be that, so it's going to go from quadrant 2 to quadrant 1 because it's a positive leading coefficient with an even degree. Okay, so it's going to be starting here and ending here, right? So when x becomes more positive, y is also becoming more positive. When x is becoming more negative, also y is becoming positive because y is going to be from quadrant 2 to quadrant 1. And then it says possible number of turning points. Well, the turning points, if you have a degree of 4, the minimum could be 0 and the maximum will be 4. Okay, you could have 4, so you could have a minimum of 0 turning sorry, I made a mistake there. For the turning points, you could have a minimum of 1 and a maximum of 3, because the maximum turning points will be n minus 1, which is 4 minus 1 or 3, and you could have a minimum of 1. Okay, so say for instance, you could have, say if your function was like this, you could have 1, 2, 3 turning points. That's the maximum you can have. Okay, or if your function was just like, say, something like this, then you could only have 1 turning point. So that's the minimum and that's the maximum. And then for the zeros, you could have a minimum of 0, no zeros, and a maximum of 4. Okay, because you have a degree 4, you could have 4 zeros. But if it never touches the x-axis like this, you could have no zeros. So you could have none also. So you can and then you can also see that in this case it's an even function. If you did f of minus x, you would get minus x to the power 4 plus 2 times minus x squared plus 1, which is x to the power 4 plus 2x squared plus 1, which is the same as f of x. So therefore this is an even function. Because it's an even function, it's symmetrical about the y-axis. So this y-axis symmetry for this function. Okay, so a possible graph could be like this. Could be like this or like this, but just see that it's symmetrical about the y-axis. Okay, and this is not the exact graph, we're just sketching possibilities, but you just have to see that you maintain the quadrants it's going to, the direction of the opening, the end behaviors, and it's consistent with what could be the graph, but not the actual graph. Okay, let's try this one here. G of x equals, I'm going to do that on a separate page here. So the second one is g of x equals negative x to the power 5 minus 3x. Okay, so you just want to add the last term is actually understood to be 0. So let's try g of minus x to see if this is an odd or even function. So you get minus of minus x to the power 5 minus 3 times minus x. So that's minus x to the power 5 plus so this ends up being actually negative, and this negative makes it positive. So plus x to the power 5 plus 3x. So it's basically minus of x to the power 5 plus 3x, which is minus of f of x. So therefore, since the g of minus x equals minus g of x, this should be g here, not f. Therefore, the function is an odd function. Okay, and so if it's it has a degree of 5 and a negative leading coefficient, so that means it's like our y equals minus x, right? Like going from quadrant 2 to quadrant 4. So it's going to start here and end here, and it could have so it's going to go from this quadrant to quadrant 2 to quadrant 4. That's going to be the end behavior. So when x becomes more positive, as x approaches positive infinity, y approaches negative infinity, and when x becomes more negative, y becomes more positive. So that's the end behaviors, and that's the answer for part A. And for B, for turning points, well, it should have a minimum of 0 turning points, because if you have a graph like the x cubed function, it has no turning points, right? Or it could have a maximum of 5 minus 1, okay, which is 4. So that's the maximum you can have, 5 minus 1. And for zeros, you could have a minimum of 1, because you know that every odd degree function has to cross the x-axis at one point, and the maximum it can have is the degree of the function, which is 5. Okay, and in this case there is symmetry about the origin, because g of minus x equals minus g of x. So whatever, so you could have, function, let's say we'll try to draw one with 4 turning points and 5 zeros. So let's say it's starting here, 1, 2, 3, 4, 5. So it has 1, 2, 3, 4 turning points maximum, right? Degree 5, and it has 1, 2, 3, 4, 5 zeros. Okay, that could be a possible graph of the function, and it's symmetrical about the origin, so that when you reflect it horizontally and vertically, it ends up looking like this. That could be a possible graph of the function. Third example we have is h at x equals x cubed plus 3x squared minus 2x minus 5. So if you did h at minus x, it's minus x cubed plus 3 times minus x squared minus 2 times minus x minus 5. And you'll find that this is not equal to negative h at x. It's not equal to h at minus, or not equal to h at x. So it's neither even nor odd. It's neither function. Okay. And because it has a degree of 3, which is an odd number, and it's a positive leading coefficient, it has to go from quadrant 3 to 1, like y equals x graph. Okay. So it's NB, so it's going to go from here, quadrant 3 to quadrant 1. So its end behaviors as x becomes more positive, y becomes more positive, and x becomes more negative, y becomes more negative. So that's the end behavior. And the turning points, well, could have a minimum of none and a maximum of 3 turning points. It's actually degree 3, so maximum of 2. And for the zeros, could have a minimum of 1 because it's a degree 1 function, and a maximum of 3 zeros because it has a degree of 3. So just going to sketch something here. Let's say it goes like that, starts here and goes there. It has 1, 2, 3 zeros, right? And it has this end behavior, and it has 1, 2 turning points. Okay, this could be a possible graph of the function. So this is just rough sketches. They don't have to actually mean that when you actually try it on decimals, you'll see it may not look anything like this, but you're just trying to satisfy these conditions. Okay, now you can try practice questions.